name is Dr. Esther Trufan, and in this video, we're going to explore Dalton's Law as it applies to some of our experiments. First, let's define what it is. Dalton's Law states that when we have a mixture of gases, then each gas will exert its own individual pressure, and the total pressure of the system will be the sum of the individual pressure of the component gases. Now, this is true as long as all of the gases behave ideally. And as we discussed earlier in a previous video, under low pressure and high temperature conditions, which we consider all laboratory conditions, most gases will behave ideally. So for the purposes of our experiments, we can assume ideal behavior for all the gases that we're working with. For ideal gases, the ideal gas law states that when we have pressure times the volume, then it will be equal to the number of moles times the gas constant times the temperature. And depending on which unit the pressure is expressed in, that constant may change. It could be either 0.08206 if the pressure is expressed in atmospheres, or 0.0831 if the pressure is expressed in bars. UPEC recommends the use of bar for pressure calculations. Most of the time in the chemistry laboratory, gases are collected over water, and these are called wet gases, which means that it's not just the gas that we're collecting, but we're also capturing some amount of water vapor that naturally occurs under the temperature conditions that exist in the laboratory. The total pressure of the gas will then be the sum of the pressure of the gas that we're generating from the reaction and the pressure exerted by the water vapor at that temperature. For the reaction of magnesium and hydrochloric acid, when it leads to the production of hydrogen, the pressure of the gas mixture will be the pressure of hydrogen plus the pressure of water vapor, because the gas is collected above water. Now, in another experiment in which we're reacting baking soda or sodium bicarbonate with a vinegar or acetic acid, the reaction produces carbon dioxide. When that carbon dioxide is collected, we have to remind ourselves that it is collected over water because the solution is mostly water. And we have to say that the pressure of the gas is the sum of the carbon dioxide and the water vapor pressures. To determine the vapor pressure of water, we can turn our attention either to some of these vapor pressure curves, in which we can take the temperature at which the reaction is occurring, let's say 60 degrees Celsius, and then we can reflect it on the y-axis and estimate the vapor pressure, sometimes in mercury millimeters, sometimes in torrs, sometimes in atmospheres. In this case, we can say that at 60 degrees Celsius, the vapor pressure of water is approximately 165 mercury millimeters. However, the simpler approach is to find a table that lists the different temperatures and their associated vapor pressures. Most of the time, we can find it in torrs because those are going to range between a small number and 760. And those can easily convert to atmospheres. And occasionally, we may also find these tables connecting the temperature to atmospheres. For the reaction of sodium bicarbonate and vinegar, the reaction that produces carbon dioxide, first, we have to identify what is provided and make sure that everything that is provided is present in the appropriate units for the calculations. Here we have a reaction occurring at 20 degrees Celsius, 0.87 atmospheres of pressure, and the balloon in which the carbon dioxide is captured inflates to 85 cubic centimeters. In the first step, we ensure that our volume is in the appropriate units. If we have 85 cubic centimeters, then first we recognize that cubic centimeters are the same as milliliters. 1 cubic centimeter is the same as 1 milliliter. And then we convert from milliliters to liters, and we say 1 milliliter is the same as 10 to the negative third liters, giving us our volume in liters as 0.085. In the next step, we ensure that our temperature is in the appropriate units. If we have a temperature of 20 degrees Celsius, we need to convert this to Kelvin, and we do that by adding 273.15 to it, giving us 293 Kelvin. We can remove the 0.15 from this calculation if we're considering the significant figures, because the 20 degrees Celsius does not have any decimal places in this measurement. Next, we're going to look at our table and determine the water vapor pressure at 20 degrees Celsius. And we're going to use the pressure in atmospheres because our pressure in the laboratory is also provided in atmospheres. So at 20 degrees Celsius, the water vapor pressure is 0.023 atmospheres. In the next step, if we know the pressure of the environment, which is the same as the combined gas pressure, and we know the pressure of the water vapor, then we will be able to determine the pressure of carbon dioxide. So pressure of carbon dioxide is the combined gas pressure minus the pressure of the water vapor, which in our case is 0.97 atmospheres minus 0.023 atmospheres, giving us a pressure of carbon dioxide of 0.947 atmospheres. Finally, we're almost ready to plug in everything into our calculation. We need to find the moles of carbon dioxide. If we know the pressure, the volume, the temperature, and the gas constant, then determining the moles of carbon dioxide should be fairly straightforward. We have the PV equals nRT expression. If we want to find the N value, then we divide both sides by RT, giving us PV over RT equals N. If we plug in our values, then for N, we have volume of 0.085 liters times the pressure, and this has to be the partial pressure of carbon dioxide, which we just calculated. That is the 0.947 atmospheres. We divide this by the gas constant. Because we have atmospheres, it's 0.08206 liters times atmosphere over moles times Kelvin times temperature. And we already converted our 20 degrees Celsius to Kelvin. It is 293 Kelvin. From there, we complete our calculation. We simplify by canceling the Kelvin, canceling the atmosphere, canceling the liters, giving us moles as our final answer. And the number of moles will be 0.00335 moles, or we can write it in scientific notation, 3.35 times 10 to the negative third moles. Whenever we perform experiments in the lab that result in the collection of gas, the simpler things to measure are volume, pressure, and temperature. The number of moles are usually implied from the amount of reactants that we are working with. So this allows us for a great tool to determine the experimentally derived number of moles so that we may compare it to our prediction from the calculations.